Question 6. Prove by induction that 2 to the power of n plus 2 plus 3 to the power of 2n plus 1 is divisible by 7 for all n values that are elements of the natural number set union 0. So that's all positive whole numbers. So the natural number set is positive whole numbers, so 1 to infinity. But it also wants to include 0, which is not technically a natural number. So prove by induction that 2 to the power of n plus 2 plus 3 to the power of 2n plus 1 is divisible by 7 for all n values. So these n's here need to be elements of the natural number set or 0. And since the natural number set starts at 1 and goes up to infinity, and 0 is below 1, then 0 would be the first number. So we're going to start off using our laws of indices to rewrite these two terms. So 2 to the power of n plus 2 we can rewrite as 2 to the power of n multiplied by 2 to the power of 2. Because we know one of our rules of indices is multiplying powers with the same base, we add the powers. So this is that rule in reverse. So 2 to the power of n multiplied by 2 to the power of 2 gives us 2 to the power of n plus 2. So it's that law in reverse. And then 2 to the power of n multiplied by 2 to the power of 2 can be rewritten as 4 times 2 to the power of n, because 2 squared is 4, and then we just keep 2 to the power of n as it is. Next, we're going to take 3 to the power of 2n plus 1, and we're going to do the same thing. We're going to rewrite that. So 3 times 2 to the power of n plus 1 is the same thing as 3 to the power of 1, so that's where that 1 is coming from there, multiplied by 3 to the power of 2 raised to the power of n. So this is another one of our laws of indices. Raising a power to a higher power, we multiply the powers. So 3 to the power of 2 raised to the power of n gives us 3 to the power of 2n. So in this part, we're actually using two of our laws of indices. So we're using the law that we used over here, multiplying powers with the same base, we add the powers, but we're using it in reverse. That's where the plus comes from. And then raising a power to a higher power, we multiply the powers. So 3 to the power of 2 raised to the power of n, we multiply the 2 and the n, so we just stick them together. Now we could have rewritten this as 3 to the power of n raised to the power of 2 as well, because ultimately when we'd multiply that out, we would still get to 3 to the power of 2n. So then we have 3 to the power of 1 is just 3, so that's where that 3 comes from there. And 3 squared is 9, that's where that 9 comes from, and that's raised to the power of n. So we have 4 times 2 to the power of n, and then 3 times 9 to the power of n. So they're in a similar format, and that's going to help us out as we move through the question. So that's what we wanted to do. We started off with these two terms, and we rearranged them, we rewrote them until they were simplified, and also until they were quite similar. So we have a term at the front, a term inside a number at the front, a number inside the brackets, and that's raised to the power of n. And then we have a number in front of the brackets, a number inside the brackets, and that's raised to the power of n. So they're very similar now. So Pn is going to be, instead of 2 to the power of n plus 2, we're going to have 4 times 2 to the power of n. Then we have our plus, and instead of 3 to the power of 2n plus 1, we have 3 times 9 to the power of n. So P of n is that these two terms added together are divisible by 7, where s is equal to 0, so our starting term is 0. So we substitute 0 in place of both of those n's, so we have 4 times 2 to the power of 0. So 2 to the power of 0 is 1, so that's 4 times 1, which is just 4, plus 3 times 9 to the power of 0. So 9 to the power of 0 is 1, so that's 3 times 1, which is 3. So 4 plus 3 makes 7, and 7 is divisible by 7, so it's true. So P of 0 is true. Next, we're going to assume that P of k is true, i.e. that is, So we'll swap each of these n's now for k. So 4 times 2 to the power of k plus 3 times 9 to the power of k is divisible by 7. So we're assuming that this is true. So we can then say that it's going to be equal to 7a for some a value element of the integer set. So some multiple of 7 basically. So we're going to assume now that this is true, that 4 times 2 to the power of k plus 3 times 9 to the power of k is equal to 7a. And if we bring the 3 times 9 to the power of k over the equal sign, it becomes minus 3 times 9 to the power of k. So we have 4 times 2 to the power of k on its own now. So 4 times 2 to the power of k is equal to 7a minus 3 times 9 to the power of k. So we're going to use this in the next part of the question. So again, 4 times 2 to the power of k is equal to 7a minus 3 times 9 to the power of k. So we worked that out in the previous slide. So remember, p of n was that 4 times 2 to the power of n plus 3 times 9 to the power of n is divisible by 7. So now we want to prove that p of k plus 1, which is going to be 4 times 2 to the power of k plus 1, so swapping that n for k plus 1, plus 3 times 9 to the power of k plus 1, so swapping that n for k plus 1, is divisible by 7. So this is what we want to prove now. So the 4 just stays where it is outside the brackets. 2 to the power of k plus 1 we rewrite as 2 to the power 1 multiplied by 2 to the power of k. So that's our first law of indices in reverse. So multiplying powers with the same base, we add the powers. So 2 to the power 1 multiplied by 2 to the power of k is 2 to the power of k plus 1. So it's that law of indices in reverse. Then we have the plus, and then the 3 outside the brackets. And then 9 to the power of k plus 1, we rewrite as 9 to the power 1 multiplied by 9 to the power of k. So again, it's that law of indices in reverse. So multiplying powers with the same base, we add the powers. So 9 to the power 1 times 9 to the power of k gives us 9 to the power of k plus 1. Okay, so now what we're going to do is we're going to swap around the 4 and the 2. We're just going to swap places, because when we're multiplying, multiplication is commutative. So 4 times 2 is the same thing as 2 times 4. So we're just going to swap places with these. And over here, we're going to actually multiply the 3 by the 9. And 3 by 9 is 27. So the 4 and the 2 swap places. So that 2 there, that 2 to the power 1 comes outside the brackets. And the 4 goes inside the brackets. But it doesn't actually change the value of the term. And the 2 to the power k remains the same. And then over here, 3 times 9 is 27. And we still have times 9 to the power of k. So now hopefully you can spot why we did that. Hopefully you can see that we have 4 times 2 to the power of k inside these brackets. And we also have 4 times 2 to the power of k up here. So we're going to replace 4 times 2 to the power of k with 7a minus 3 times 9 to the power of k. So the 2 stays the same. We have the set of brackets, and we bring down the plus 27 times 9 to the power of k. Next, we're going to multiply out these brackets. So 2 times 7a is 14a, and 2 by minus 3 times 9 to the power of k is going to be minus 6 times 9 to the power of k. And we'll just bring down the plus 27 times 9 to the power of k. So 14a, that's the only a term we have, so we'll just bring that down. And minus 6 times 9 to the power of k plus 27 times 9 to the power of k is going to be plus 21 times 9 to the power of k. So we have 14a plus 21 times 9 to the power of k. So we're going to factorize. So remember, going back to our question, we want to make sure that this is divisible by 7. So we want to make sure that this is divisible by 7. So we're trying to pick out a 7. We want to factorize out a 7 so that we can show that 7 can divide into it. And we can do that indeed. So factorizing, we can take out 7 as the highest common factor. So 14a divided by 7 leaves us with 2a. And 21 times 9 to the power of k divided by 7 leaves us with 3 times 9 to the power of k. So it doesn't matter what's inside the brackets here, we're going to just call it b. So we end up with 7b. for some b element of the integer set. So it doesn't matter what this is, it's some positive or negative whole number. So we end up with 7 times b, or 7b. Thus, p of k plus 1 is true, assuming p of k is true, which we did on the previous slide. And hence, p of n is true for all n values elements of the natural number set, but also including 0, as we already proved.